Hello, my name is Tom Elliott, and I thought I'd do a one on aviation here a little bit, talking about stalls. It appears that, well, we've known about aircraft stalls. It's taught in all your elementary aerodynamics courses, your pilot training, and everything. We still seem to have a lot of accidents with stalls. And these are not just from inexperienced pilots. This happens with professional pilots, both in airlines, corporate, and military. And it appears that when someone has a aircraft that is stalled, it's near the ground, the nose is approaching, they instinctively pull back on the yoke. And the airplane just does a full stall and will crash. There is techniques looking at it, what we call upset training and prevention. And the FAA's looked at a study in that. I will get more into that study later. Today I'm just going to talk a little bit about stalls. There's been some cases of some 737s, several of them, that had rudder hardovers. As the airplane did that, the airplane rolled off to the direction of whatever the rudder was depressed. As the nose dropped, the crew pulled back on the yoke, and this shows up in the NTSB accidents and some of the recreations of the accident. You can actually see the controls, the yoke, because they get this off the black box, that this stick is all the way back, all the way to the ground. So let me start off talking a little bit about what causes a stall on an aircraft. So what I'm going to start off with is looking at a wing, or an airfoil in this case. As we look at a wing, and we'll take a look at a wing or an airfoil that is not moving at all. And if we look at it, we have atmospheric pressure coming down on the wing. It comes down, it's all over all the surfaces. Now, what happens if we look at a venturi? This will help explain some of it. As air passes into a venturi, it causes this air to speed up. As it goes through this venturi, there's also a reduction in pressure. So if I split that right there and look at it, as air comes and flows over the wing, we're going to get a pressure, in other words, a reduction in pressure on this, or actually pressure coming upward off of it. And we're going to have a tangential force right there too, and we're going to sort of not discuss that right now for the purpose of this discussion. So as you can see, as this air flows over here, we get this force coming up off the surfaces. And we get the same thing here. As the air comes across here on the bottom portion, we get a force coming this way and this way. So what does this all do? Well, what it really does, since the air is flowing faster on the upper surface of the wing, as air is flowing over the upper surfaces of this wing, it is actually going faster than the portion down here. Therefore, if we take a look at a summation of all the forces, and this is a chord line which goes from the leading edge to the trailing edge, and there is a point here called center of lift. We're going to add up all these forces here, and we will find that we have, off of this chord line, a force, resultant force that's perpendicular to the chord line. Now, how does this lift change? Well, as we increase our angle of attack, and the angle of attack is looked at is from this chord line projecting out and a line coming into it. This is the relative wind. This angle right here is angle of attack. The more I increase the angle of attack, the more the coefficient of lift increases. So we get an increase in the coefficient of lift as we do this. And this lift generated becomes greater. Also, as we step back on that and look on it, as this thing is tangential, this is going here, here's our line, you'll find if we look at it
this direction, this lift is here, we have the vertical portion. We're also getting a horizontal portion. That horizontal portion is actually called induced drag. And the upper portion, of course, is our lift. Now, there's many theories about how lift is generated, but typically, looking at this, it is actually generated by the flow across the wing. There was some talk about a downward force and momentum and stuff. Those are the result of the product of the lift. Lift itself is generated by this, is pretty much what the experts have to say. I've got a real good book, and I'll show a picture of that. And that is referred to, it's called Flight, and it's by John Anderson, which is an aerospace instructor. He has a doctorate's degree, very good, and he's published a lot of books. So looking at that, and I'll use this theory here, this explains a little bit what causes lift. And continue with our discussion here. This is the book that I'm referring to. It's called Introduction to Flight. This is the 6th edition book. There's also, I have an 8th edition, and I think he's up to edition number, or the 9th edition. His name is John D. Anderson Jr. He has some excellent books he has written. Well, this is written for the people that are in aerospace engineering, either the first or second year. It is very readable. There is some math in there as far as calculus. And you can sort of read by that. And he has very good explanations. So I would suggest anyone that's really interested in how it's the modern way of looking at how aerodynamics work to obtain a copy of this book. It is available on Amazon. The other thing I want to talk a little bit about is this is the formula for lift. So lift is equal to 1/2 rho, which is the density of the atmosphere at the place. S is the surface area of the wing or airfoil, and velocity squared. So we can see that we generate more lift. And one of the things I do have missing in here is the coefficient of lift. So we would actually have a coefficient of lift in here also. But what it is, this is basically how we're going to get our lift formula. So we can see here a couple of ways that we can generate more lift on the wing. We can either increase the velocity, assuming that these are constants here. The wing doesn't change shape. It can in certain cases. The density will change actually as you go up in altitude and the air gets colder or hotter. The temperature of the air makes a difference. So those will change, but for our purposes of looking at right now, we're looking at it a constant atmosphere of maybe 1,000 feet above the ground or something. Surface area is not going to change. It's pretty much standard airflow. So we've got the variables of the velocity squared and the coefficient of lift. So what does this really mean? How do I change the velocity? Well, it's just change the speed of the airplane. But as the speed of the airplane increases, it's by the square of it. So the faster I go, so if I double my speed, I'm going to increase my lift by 4 times, just so it's the square of it. Coefficient of lift. Now what is coefficient of lift? We talked a little bit before about it, but coefficient of lift generates off of our angle of attack. As we look at a wing and looking at a curve on here, as I go up on this, increase my angle of attack. As the angle of attack increases, you'll see that the lift comes up, and then it gets to a point and it sort of drops off. And if we look at this coming across in here in degrees, this will show it, this is our total lift off that wing, or coefficient of lift in this case. So the higher the coefficient of lift. But once we get to this point up here, we no longer generate a smooth flow over the wing surface, it starts dropping off. Well, if I look at a wing and a airfoil, as I bring the wing up as air comes across and flowing over this, the higher this angle of attack gets to be, the air will stop flowing smoothly across here and will start burbling backwards. If that's the case,
then we're actually going to get into a condition called stall. Where do they occur? They probably occur around 15 degrees, typically in a wing where it will stall at. This is a normal wing. Once I get that separation, in order to recover from it, I've got to reduce my nose or reduce the angle of attack. As the angle of attack is lowered, it probably takes about 4 degrees to come down to establish that flow back over the wing. So as the air is coming down burbling, I have to have enough flow to force it back down. So on stall recovery, basically, if you stall the aircraft, the only way to recover from it is reduce angle of attack. So talking about it, how many angle of attacks can a wing stall at? Well, typically, if it's in normal flight, it's not going inverted, the flow across this wing is going to have one angle of attack that stalls at. Once you exceed that, you've lost separation on the wing, the airplane starts going to be in a full stall condition. It does not matter where the nose of the airplane is pointed. It can be pointed straight up, it can be pointed straight down. A lot of times we refer to getting out of a stall or doing it is unloading the wing. What that means basically is I reduce the angle of attack, the loading on the wing is not as great, I get established flow back across here, and the wing is flying. Can I stall it at any airspeed? Yes, it can be stalled at any airspeed once you're airborne. On the ground, obviously, the weight's taken by the wheels, but once you're airborne, if I'm at stall speed, and normally what they figure on the stall speed in aircraft, they'll take the weight, and then the weight in the, you'll look at it, and then you'll turn around and see a speed for a certain gross weight of the airplane. Well, this is based on 1G. And when the airplane keeps coming up, it gets to this point of critical stall. They publish that in most of your flight manuals. You'll also notice that we also increase them. If I increase the angle of bank, and if I go into a 60-degree angle of bank up in holding level, it'd be 2 Gs. And you'll see that listed also. A lot of times different angle of banks, how much speed it takes to maintain it. Now that's assuming the wing is at this, if I at a certain loading. So if I reduce my loading on the wing, reduce it to half by pushing forward on the stick, then it will turn around and stall speed reduces. So what does this all mean? If an aircraft stalls, push the nose forward. Now, we talked about this as in normal flight. If I'm in inverted flight, it just reverses because the airflow is coming back and the airplane is upside down and it's trying to hold the nose up there, so I've got a reverse flow over it. And that's going to also have a negative angle of attack. Can I have that in normal flight? Well, it doesn't really matter. If I take the airplane, push the nose down like this strong enough, and the air's flowing over here where it's a negative, I've got negative G's, I can actually stall the airplane negatively. To recover from that, because the stick would be forward, I'd have to pull back. So there gets a little bit of understanding here of misunderstandings actually of what really occurs. Now, where do you learn a lot of this and see it? Well, if you've done some aerobatics and had aerobatic training, you'll see how some of this stuff works. Most people that I've talked to when I've given ground schools and stuff, I usually ask people, okay, have you had the airplane upside down? And I used to teach at a training center of flight safety is where it was, and I'd give ground school and simulator instruction. So we'd talk about some of this stuff in class, and I'd ask people, well, how many of you people have actually been upside down? And a lot of people have not. So what does this really entail? Well, if I stall an airplane and I'm got it into a condition where it's stalled, I'm loading the wing up, then what am I going to do? Well, if I'm stalled and it's near the ground, typically you get a tunnel vision will come in, your vision narrows. Of course, adrenaline comes in, is what's causing this. And then people have a tendency just to pull because they see the ground coming down. I want to pull up on it. The only way you can recover from that is push the nose forward and break the angle of attack. We'll talk a little bit, I'll give a class and talking about some of the stuff the FAA has and show some of their slides in a future edition of this. So anyway, talking a little bit about stalls right here and why they occur. Now, what do I really need to know as a pilot?
I'm getting a little deep into this, and a lot of the aerodynamics and stuff is really, do I need it really to fly the airplane? Well, you need an understanding of it, not so much flying it, because we'll take care of that. It's a good idea to have it academically. The other thing that caused us a problem is that the FAA, they used to call it the practical test standard, now it's the ASA, what they use for doing flight tests. Well, one of the conditions was that the FAA, a lot of airplanes, they have stall warnings. These stall warnings are typically in a jet airplane will probably come on 5 to 10 knots before the actual stall. When this occurs, they want you to do a stall recovery. Well, the airplane's really not stalled, and the way to get out of that is, of course, to lower the nose, reduce angle of attack, add power, and the practical test standard said we needed to have a minimum loss of altitude. They didn't really specify it. In these training centers, people found, and the instructors did, that they could actually power out of one of these approaching a stall. Because what happens is the airplane is not stalled. I add full power and I keep my nose here level. Then as the airplane starts to accelerate and I keep the nose level, it will increase speed. Angle of attack is also reduced. Because of relative wind, you're not falling, eventually you'll start a climb. So the relative wind changes. Not the proper way to do a stall. It was the stall recovery was trying to show, okay, we're approaching a stall, how do I recover with minimum loss of altitude? FAA has gone back and talked about that, changed it because there was a lot of stall accidents. People were in simulator training, which a lot of people do for jet aircraft. It's pretty much the norm right now. But if you only go to training, depending if you're a 121 pilot or a air taxi or a 135 pilot, you might do that twice a year, sometimes only once a year on the training, taking checks. If you're in corporate aviation, you're looking at a 6158 check. Typically that's done every year in some type of type-rated airplane, and at least every other year in the type rating that you're actually flying. So if you're flying two types of type-rated airplanes, let's say you're flying a Citation and the other one's a Learjet, well, you can alternate. So your training, you may only come to training class for once every 12 months. During that, typically you get about a 3-day session, 6 hours or so in simulators and doing the training. So you go back through, do this, show proficiency, and you're good. But that's the basis of your training. And like I say, you're doing stalls. You usually typically do them at altitude in simulators. It's the way it has been. You get the stall, you get the buffet, again 5 to 10 knots before the airplane actually stalls, do a recovery, looks good, good to go. Does that really happen in real life? Not really. Stalls occur, pilots get distracted, stall occurs. And like I said, if it's near the ground, people have a tendency to pull back on the yoke because they fear hitting the ground.